All right, good morning, everyone. Thank you for being here. We're the early risers, I guess. So I'm Joe Flasher. I'm the Open Geospatial Data Lead here at Amazon Web Services. And so what that means is I work with a lot of our customers across public sector and commercial sector and globally to help them figure out how best to use the cloud when working with geospatial data. So one of the ways that we do that is through the Public Datasets program. You can find a lot more about that if you just go to opendata.aws. But one of the purposes of the Public Dataset program is to help groups figure out best practices for working with data in the cloud, and then to also democratize access to data, right? So the reason why I'm very excited to be here in this session is because the SpaceNet initiative aligns very well with that, right? So it's my belief that access to resources, compute resources, to meet large-scale ML challenges is becoming commoditized, right? So everyone can have access to large amounts of compute power and tools to do this work, but the knowledge needed and the training data needed to successfully meet these demands is becoming unevenly distributed. So I'm super excited to be part of this initiative and for you to hear about this more in a little bit, because it meets one of the goals of our Public Datasets program as well, which is to get more information and more knowledge into the hands of more people. So I'm going to stop now and let the people who know more speak to you. So I'm going to turn it over to Ryan, Todd, and Adam to tell you more about SpaceNet. Thank you.
All right, well, thanks, Joe. So my name's Ryan, and today we're going to walk you through just an overview of SpaceNet and sort of our logic in standing it up. And then Adam will walk you through some of our previous results, as well as challenges that we're looking to host this year and in early 2020. And so I think one of the things that's really important to start with is, why did we even do this in the first place? So Joe mentioned, a need for putting out training data and a need to have greater focus in the research community on geospatial problems. And I think one of the general takeaways for us, both inside In-Q-Tel as well as for all the SpaceNet partners, is that we really view the emergence of sort of the computer vision algorithms along with new data collection techniques in the remote sensing domain. We really view these two trends as sort of a way that is going to fundamentally disrupt what's happening in the geospatial domain today, right? And when you think about it, that's really important. And sometimes this gets hand-waved away when we look at all of the really compelling results that are coming out of some of the most recent computer vision conferences in terms of some of the performance metrics we see. And while those results are impressive, it's very different when you start talking about applying these techniques to very hard problems in the world today. Right, so as an exemplar, if you look at the open mapping effort that occurred after Hurricane Maria, this was specifically led, these numbers, to be precise, was led by Humanitarian OpenStreetMap. The numbers kind of speak for themselves in terms of, one, just the size and scope of the need in terms of building foundational map information after a disaster, as well as also speaks to how labor-intensive these efforts are. And the sort of big takeaway for us, and one of the primary motivators, is if you look at just the days to complete the entire maps to be delivered out to the American Red Cross and other first responder groups, 70 days, while impressive in its own right, is really inappropriate if you think about what a first responder group would need. Right? They need information in the order of hours, not in terms of days. And so the question for us is, well, why haven't we seen more computer vision or machine learning work make its way into these applications? Essentially, what's holding us back? Right? And there's a couple of reasons. One is that sort of ImageNet, which was really one of the foundational pieces for driving a lot of the open source computer vision research, was great, but it's very different. It's a very different data set than satellite or drone imagery. And so building models on that and then transferring it over to either object detection or feature extraction for mapping, those are very different problems. The second of which is a lot of the models which are deployed today and that are available, right, in all the different frameworks, right, those were built, once again, on ImageNet data sets. So identifying a cat or any of our other favorite features or object classes in a photo is very different than extracting hundreds of thousands of building footprints in a satellite image. It's a different problem. And so for researchers, what that means is, as any of you who have worked in this domain know, you're almost starting from scratch. And then last but not least, and sort of the third hurdle is that we say this all the time in preparation for this panel, we were joking about it, geo is really hard. And one of the things that makes it so difficult is that although there's been a lot of advances in the open source software and proprietary software that's available to spin up models and then deploy them, it's still in its early stages. And so if you're a researcher and you're thinking about what problems you want to start in, or if you're a startup, or if you're a mature technology company, you're going to look around and say, can I get curated labeled data? Well, probably not easily. Are there models that I can at least start with and then tune for my specific problem? Well, there weren't. And is there a software that's been sort of proven to deploy all these solutions? Well, there isn't. And so you kind of see these three hurdles and you go, well, why would I focus on this problem and spend the next year trying to figure this all out when there's probably something that's lower hanging fruit? And so collectively, our takeaway was, well, what can we do to help the broader community focus on these problems and maybe knock down some of these hurdles? So our takeaway was to model ourselves after ImageNet, but focus on overhead data. Thus, we helped form SpaceNet, which is it's hard to believe, next month will be its third year of operation. We're structured as a nonprofit LLC to target these three areas to essentially knock down those challenges. So our goals is to put out data sets, to host public competitions and open source algorithms from those competitions, and then last but not least, post out and publish a robust amount of research, not just evaluating the algorithms from competitions, but also giving our collective thoughts about what we see next in either the software or algorithmic development space. And what's really compelling about all this is that it's really a combined effort. So Cosmic, that's an applied research lab within In-Q-Tel. AWS, Joe's team has been essential in putting out those data on public internet. Intel AI has been helping drive our research, and both in publications as well as some of the code development. And then Maxar was really the group that helped us get it all kicked off in the early days before we even had a name for it, in terms of putting out data, having those data labeled, and then analyzing the results from competitions. And so there's really four key takeaways for SpaceNet. So we call them pillars. The first of which is, as Joe highlighted, we're putting out labeled data sets. Right? This is sort of the foundation, if you will, which is right now we have six cities. These are full image strips provided by Maxar. And each one of those image strips is over a city in the world. Right now, we have a little over 800,000 building footprints, and we have a little over 10,000 kilometers of labeled road to follow the OSM standard. Joe, is there a piece you want to add here on just how people can access it and how we set it all up?
Yeah, so this data is made available through our public dataset program. The data stored on our object store called S3. And then there's one sort of interesting technical piece that we've sort of iterated over in time. Due to the nature of the data and particularly the imagery, there are requirements on who can access that data. And so it was interesting because what we sort of determined within the group was that as long as those customers, the people trying to access the data, had an AWS account, they actually met the requirements for being able to access the imagery. So then we had to figure out how can we force somebody to have an AWS account to access the imagery, which is not something, if you're familiar with our public datasets program, most of those datasets are just completely and freely available, right? So there's no sort of friction to accessing the data. And so the first thing we did was use a requester pays bucket, which if you're familiar with S3, it basically forces somebody to authenticate as the user, and any egress gets charged to the user. But that was putting a fair amount of friction in front of the data and what we wanted how we wanted groups to be able to access the data. And so we actually went down a bit of a rabbit hole, and what we came up with was a bucket policy that essentially forces the user to provide an account, an AWS account, when they access the data, but it doesn't have anything to do with any of the charges, for example, right? So the way that the data is currently available is there's a bucket policy in front of it that as long as you provide an AWS account, you can access the data for free, right? So there's certainly no charge to purchase any of the data, nothing like that. But there was previously a charge to egress the data out of AWS, but that's no longer the case. So this is sort of a good, I think, a good compromise that we've come to across having somewhat of a frictionless access, but also meeting the requirements that we have for getting the imagery into the hands of users.
Yeah, and one more thing to add to this, and this is something that Todd likes to point out, is that when we were first releasing both the full image strips as well as the labels associated with those images, we had a lot of feedback from the community about the right way to license it. And I think it's a major lift for us, and special thanks to Maxar, for having a Creative Commons 4.0 share-alike license, so these data can be used both by researchers and academic institutions as well as companies. On the competition side, to date, we've hosted 4 competitions on Topcoder. We've received over 1,000 submissions worldwide. Right now, it's at about 40 countries, or participants from 40 countries. Todd's going to walk you through some of those competitions in a little more detail. Adam will walk you through results from SpaceNet 4, which was actually led by one of our colleagues, Nick Weir, here in the front row. With each competition, we also offer a cash prize. The total cash prize is $50K spread out across the top 5 winners. From those competitions, we will open source the winning algorithms. So to date, we've put out 18 algorithms on the SpaceNet GitHub repository. Specifically, that means there's 13 algorithms for building footprint detection, and then there are 5 for road network detection and routing. And last but not least, one of the things that we have tried to provide iteratively over the course of these competitions is associated software tools to make it easier to spin up these models. You know, and one of the things, right, that we take a lot of pride and excitement in is that with the use or expanded use of SpaceNet, we're starting to see more geospatial-oriented data sets become available to the public. And this is great because for a couple of reasons. One, it means that the research community that's focused on this particular problem is growing, which is great. And 2, with that momentum, it starts building a broader discussion around core topics such as data standards and cataloging standards. And for those of you who follow any of our blogs or anything like that, just last week we were supporting the STAC sprint, which is the spatiotemporal asset catalog. So I would say one of the things that's been great is by having more participants, we're starting to get feedback such as, well, how do I search the repository easier? So I think that's something that we're going to continue to push on as we focus on SpaceNet 5 and 6. With that, I'll turn it over to Todd to talk about all of our competitions and some of the metrics we've pulled over the last 3 years.
Great. Thank you very much, Ryan. So as Ryan said, I'm going to take a deeper dive into the pillars of SpaceNet. Ryan talked a little bit about the number of data sets that we've released so far, as well as you can see some of the other data sets that have been made available within the community. So that was first and foremost the important thing that we wanted to do to get data out so that researchers could actually use this data and start to write papers with the data. We also launched a series of competitions to help accelerate innovation using the data sets, as well as generate interest and excitement within the community. As we thought about ImageNet as our inspiration, this was another aspect of ImageNet that we thought could make a lot of sense in the SpaceNet context. So the first competition, we focused on building footprint detection. And as Ryan alluded to earlier in his opening remarks, we thought about kind of applications of this technology and how computer vision algorithms could be applied to satellite imagery or remote sensing data. And we thought about what tasks were very manual amongst the mapping community. And we looked at platforms such as OpenStreetMap. These are platforms where there's great community collaboration. Many of the first features that are digitized are infrastructures of building footprints and roads. And we thought, well, if we release this data set, this could be something that we could help to automate some of the basic mapping that takes a lot of time for human mappers or labelers to produce. The Rio data set was actually originally part of a open data set that we had released around the Rio Olympics. So we started with that. We learned a lot from that challenge, and both in terms of the type of satellite imagery, the resolution, as well as how the imagery was processed, as well as then the type of the labeling methodology. So we had building footprints that were more comprehensive compared to what was publicly available on OpenStreetMap. But we also learned that labeling consistency, completeness, and accuracy, of course, really matter when it comes to training algorithms. So within SpaceNet 2, we continued on this theme of foundational mapping with building footprints, but we released, instead of 50-centimeter satellite imagery that was mosaicked, we released 30-centimeter worldview imagery that was a single image strip, so to control some of those variables. We also released 4 different areas of interest across 4 different cities to create geographic diversity so that the algorithms wouldn't be just as localized to one city. And then we improved our labeling methodology as well. So all the building footprints on SpaceNet 2 were fully hand labeled to, again, get that, the completeness, the consistency of labeling methodology, and the accuracy of the labels. In SpaceNet 3, we wanted to expand beyond building footprints and look into another aspect of foundational mapping, and this was with roads. So this actually dovetailed quite nicely on the 4 AOIs that we had labeled with SpaceNet 2. So we produced road labels for these 4 AOIs within these cities as well. And Adam will talk more about the metrics that we developed around how to measure the algorithms that were developed for SpaceNet roads. At SpaceNet 4, we went back to building footprints, but we looked at this through a very different lens. So the founder of Digital Globe, who's now the CTO of Maxar, Walter Scott, he had challenged us. One of the things he asked us to look at was our next generation constellation, the WorldView Legion satellites, are going to have much higher frequency revisit. And one of the characteristics of this type of imagery that we'll have to handle is higher off-nadir angles. So in other words, the satellite imagery may not be collected as close to pointing straight down. And we wanted to test how resilient these algorithms would be from a performance perspective and what that performance threshold might look like. So that was the focus of SpaceNet 4. We produced the building footprints and measured them against it. So we'll hear more about that as well. As I mentioned, we looked at the pillars. So the algorithm development and release is part of this. This is the result of the challenges. We've also tracked the performance of these algorithms over the course from SpaceNet 1 to SpaceNet 2, SpaceNet 4 around building footprints specifically. And what you can see is, so using the intersection over union metric with F1 score, you can see how this performance has improved over challenge. Now, there have been some differences in the data sets, but we think that this is, as this community has gotten more familiar with both remote sensing data and ways to improve performance, we've been able to see marked performance over the course of these challenges. So we also track performance, in terms of the amount of data that we've been able to release and how much this has been accessed. So you can see from the first box there that this data set parts of the data set have been accessed almost, so 347 million downloads of different parts of the data set. Over 267 terabytes of data. This, of course, is all made possible with our partners from AWS, having the data set being hosted as part of the public data sets within the Earth imagery part of this. And so this was important. We were also able to have the requester pays removed, so this data can be accessed by researchers to get the data without having to pay for any sort of transfer costs as well. We also have maintained a commitment to open sourcing the algorithms as part of our pillar as well around the algorithm development. These are the results of the SpaceNet challenges that I talked about. And you can see the engagement from the community around it, number of submissions, as well as international participation, as well as the software that we've also produced to help lower the barrier to entry in the baseline algorithms within our GitHub repos. When we think about this in an international context, so you can see the top countries that have accessed the data sets. This is in many ways not surprising. These are some of the top countries where we're seeing a broader leadership around AI ML work. But we wanted to look at this through the lens of SpaceNet as well. And then, we've referenced ImageNet a couple of times in terms of our inspiration for this project. But one of the things that we were absolutely thrilled to see, and Adam snapped this picture, so I'll make sure I give him credit for it. But Dr. Feifei Li at CVPR in 2017, within her talk, she actually referenced SpaceNet, which for us was, given this was something that we were inspired by ImageNet, we were thrilled to see her reference this. And I think as we look at SpaceNet and the impact it's had, this is something that is part of a broader trend of we're seeing more applications of computer vision into both vertical specific areas, as well as going from not just within these sort of algorithms and data sets within computer vision, you're seeing there's MusicNet, MedicalNet as well. So the theme is that that this idea of having open data sets to advance AI ML applications, as well as then perhaps challenges in these areas, this is helping to advance the state of the art. So with that, I'll go ahead and hand it over to Adam.
Thanks, Todd. What's my button? There we go. So I'll go into a bit of a deeper dive onto the SpaceNet 4 results. Right, this is the off-nadir piece. And I'll reiterate that I'm standing here as more as a proxy for Nick, who really ran this and did a lot of great analysis. And so we're getting into the data set. So it was a really unique collect, right? 27 different collects over Atlanta in the span of a few minutes. So there's really no change in the infrastructure there across the time. And this was a calibration shot. But as the satellite passed over, we took these 27 different shots. And this covered 655 square kilometers at 0.5 meter resolution, so pretty unique collect. You can see in the middle, right, this is this kind of little GIF about how the stadium looks as you pass overhead. We labeled this, all the SpaceNet labels have been hand labeled and validated, so it's a pretty high quality data set. That's one of the things we're most proud of, is this the quality of both the imagery and the labels. So we did quite a few building footprints. And then, as usual, we ran a competition around this, open sourced the algorithms, and then put those up on GitHub for people to use if they want to explore more going forward. Why off-nadir? So there's actually a couple good reasons, right? One, perhaps most obvious, is that in a disaster scenario or emergency response, the first image of an area is often highly off-nadir. Maybe there's clouds, maybe just the orbits aren't quite right. And in this case, this is the earthquake and subsequent tsunami in Japan, right? It knocked out the reactor, and the first shot was 45 degrees, right? So if you can't analyze these off-nadir images, you're really missing out on something that might be really useful. And so that's one of the primary motivations. The other one is something that Todd mentioned earlier, which is this idea is a kind of a proxy for revisit rate, right? So a lot of these constellations being built right now, right? One being Max Har's Legion, there's Black Sky, there's Planet. There's a lot more satellites going up, but there still won't be enough that you can just revisit very quickly without slewing off nadir. So if you really want to study high revisit rates, you need to look at actually can you analyze off nadir imagery. And what's usually done, state of the art in research, is looking straight down. So it's not something that's well addressed. So this is something we figured maybe we'll take a crack at, see how people handle this problem. So there's actually a few barriers to off nadir that make it pretty challenging. One is just shadows. Shadows change depending on your look angle. Footprint displacement's another one, right? So as you're looking at an angle, that footprint will be displaced from what you saw originally. There's things that are occluded. So this bottom left image, right? I mean, the skyscrapers completely occlude some of the buildings behind it. Can you handle that? And then resolution degradation, just simple geometry, right? As you're looking way off angle, your resolution starts at 0.5 meters, ends up around 1.7. How does that affect your algorithms and your performance? So what we did for scoring was kind of also inspired by ImageNet for their eventual competition, which looked at object detection. And it's an IOU metric, so intersection over union means basically your proposal and your ground truth, how does that intersect? 0.5 or greater, we call it a true positive. And it's a knob you can turn. So we have here just showing on this left image is ground truth in blue. And if you have a proposal in red there in the middle, you have an IOU of 0.75. So that's a pretty good idea of what the building looks like. On the right, 0.15, we call that a failure. So again, this is a knob you can turn. And again, 0.5 is kind of the threshold that's standard across the community, but this is something that's good to know because if you really need very precise footprints, maybe you need this threshold much higher. Whereas if all you need to know is maybe just where the buildings are in a rough count, you can lower this threshold, right? 0.5 is a good medium, and that's what we used for this competition. We had these 27 different collects from all sorts of different angles. We bin these into 3 different bins, so we called Nadir 0 to 25 degrees, off Nadir 26 to 40, and then anything above that, very off Nadir. To score that, we average these bins, and that's the score that we'll report. So some challenges for the Nadir angle, right? If you look at just Nadir, so looking straight down, 7 degrees is pretty much close to Nadir. That was the close Nadir we had. The scores here are really pretty good, right? So 0.8, a little above 0.8, but we have a significant drop of 40% or more as we go out to 54 degrees. And this curve, I think, illustrates a couple things. One, that the performance of the different competitors was pretty tightly clustered, for one. And then also the magnitude of the drop-off is significant, right? So if you need a building footprint and your first look is at 54 degrees or 45 degrees, you're really gonna have a challenge of pulling out a precise footprint. So this is something where we're really excited about machine learning, but we would not call this a solved problem quite yet, right at the very off Nadir angles. There's also this interesting sawtooth pattern, which we'll show a little bit more later. So that is caused by something that we didn't really think through a whole lot, but again, once you dive into the data, you see, well, so some of the shots are taken from the north, some from the south, right? And so if you're looking from the south in the northern hemisphere, right, you have pretty good lighting. Looking from the north, it's kind of backlit. And that actually causes problems both for the human eye, but then also the algorithms. And so we saw this dip, these red arrows, when you're looking kind of into the sun, right? And you see this degradation performance. So that's something that's also important to know perhaps going forward. If you train your model and don't ever have something that's looking into shadows, you might expect a much lower performance. Another issue is occluded buildings, right? So this is Atlanta, there's lots of trees, and also other buildings kind of blocking you sometimes. So how does we perform? So again, there's 2 curves here. The red is occluded, and we see a similar shape, but again, a significant degradation in performance if you have occluded buildings. And so I'm going into a lot of detail here, and there's, I think one of the reasons is that as researchers, right, there's certainly a incentive often and a kind of a push from the community to just find a score, report it, and say, you know what, the score we got was 0.01 better than what's previous, call it good, call it a day. But kind of as we've seen, and again, Nick did a really good job digging into details, is there's a lot of meat you can get to if you dig into those scores, and a lot of subtleties. And our goal really within the SpaceNet community is really to try and make this more applied, right? So all these things we're hoping are something the community can take away and use going forward, and not just that our F1 score was 0.66, right? Another one is building size, right? So there's a lot of variation in the building size. This is on the x-axis here is a log scale. So you'll see there's a huge difference in building sizes. And we see the scores increase markedly as you get to larger buildings. Not too surprising, but quantifying this is pretty important. So you can see, right, once you get to a building size of about 120 square meters, your score is much, much higher than if it's lower. This is something that could be very useful to know in a lot of scenarios. And then finally, an issue I think it's fun to dig in here to the scores is that this footprint quality threshold matters, right? So we talked a little bit about IOU before, and that a 0.5 score is something that's standard in the computer vision community. But if you really want, say, square edges and something like you might expect in an actual map you might buy, you need a very high IOU score, right? So a 0.5 is going to give you kind of a blob that's going to be roughly the area of the building and the right location, but it's not going to give you like the actual corners of the building, right? And so if you look here at the performance, as we up this IOU threshold to something like 0.9, right, our scores are just terrible. And that's good to know exactly where that falls down because, again, if you want to actually build really nice maps, machine learning still has a little ways to go. And we've looked at some of the outputs of other researchers, right? And the SpaceNet folks did a good job, and they're actually more or less state of the art. So this is something that is pretty, it's pretty interesting, but it's, again, not quite solved. And so I think there's a lot we can still do to try and pull on this problem. If you'd like to know more about all this, of course, we have some blogs up, but then we have a paper that's out as well. You can dig into some more details on this. Upcoming challenges. The next one we're doing is roads, but in order to give you a little background for what we did for what we're going to do for roads, first we'll discuss a little bit about SpaceNet 3, which was also roads. So finding roads from overhead imagery or satellite imagery is not a new concept. People have been doing this for a while. Some really, really interesting work there. But what people typically do is measure the pixels. So you'll say a pixel is either road or background. And then you measure yourself based on that pixel mask, right? And so that's a little toy example we cooked up here where maybe the green is your ground truth, and then you have two proposals, one in orange, one in blue, and you're scoring with these pixel-based metrics. What this shows is that the orange one in the middle there, the widths are incorrect for the road predictions, so your scores they're okay, but they're not great for all these different metrics. The one on the right, the widths are correct, so you actually get a higher score for this. So your metrics that are pixel-based are incentivizing this rightmost blue proposal, which obviously is a problem, right, if you're actually trying to do something useful like routing maybe. And this is common, right, because you have overhanging trees or maybe buildings or overpasses, and so you have these gaps very frequently occur in these predicted networks. And you don't want to incentivize, I think, this rightmost behavior because, again, these gaps in the road are problematic. There are some metrics which do look at kind of the graph structure. They didn't really do exactly what we wanted, so we ended up actually trying to cook our own. So this is another example of some of the state-of-the-art papers out there doing road detection and some pretty compelling results. But it's probably maybe hard to see, but they all kind of suffer from this issue of there are gaps in the network just because it's hard some places, shadows, but the scores reported is extremely high. So you might take these papers and say, you know what, it's pretty close to solve problem, but if you're doing kind of connectivity, it's not quite a solved problem in our estimation. So we took this idea of graph theory, and that there are some other ones out there, as I said, so Topo, SP, some other ones, they're so new they haven't been named. And we ended up saying, look, what do we actually care about for pulling out roads? Well, we care about routing, right? And shortest paths. So we're just gonna build a metric based on this. So we'll say, look at the ground truth network and the proposal network, compare shortest paths between points of interest, and then compare the lengths, and then measure the differences, and that'll sum up to be your score. So that's the gist of this metric. It's based on graph theory, which is what you care about, right? Graph theory is nodes and edges has to connect, and so highways are graph structures. So that's the metric that we've used to try and measure this competition. And then, so the exciting piece there is, right, since we're actually measuring based on a graph structure, we force the competitors to give us a graph structure, so something a little more useful than just a bunch of pixels. So really quickly, kind of the standard approach that we did for our baseline and something that was emulated by the competitors was you start with kind of this deep learning segmentation model, and you augment, build a buffer, et cetera, and then you get a prediction mask. So this is the bottom right. This is where you often end, kind of in a lot of current research, and that's not really as useful as you'd want, so there's a few extra steps you might do. Take this just pixel mask, so pixel mask, right, just a black and white image, grayscale, and then refine it, and then maybe you get actually a network out. So this is what we're showing here in the bottom right. This would be a proposal that we would submit and say, you know what, let's score that proposal based on the ground truth and see how we do with this APLS metric. So this is what we did for SpaceNet 3. We ran this, and we actually were pretty impressed with the scores. So 0.66 was the winning score. Also, there's a very small variance here if you look at the top 3 scores. Also, you look at the international aspect here, right? So people from all over the place scoring well. So Russia, France, Germany, USA, India, Norway. So that's pretty exciting. And you'll also see there's variance in the scores between different cities. Not too surprising, Las Vegas is a lot easier than something like Khartoum. So here's an example of Las Vegas. And on the right, you'll see this is a very good proposal, right? The blue is ground truth, the yellow is proposal, and there's a lot of overlap there. We see a very good score. On the left, again, a lot of overlap. It looks pretty good, but you miss this critical intersection in kind of the center of the graph. And so you have actually a pretty poor score because that's important, and so it's something that will penalize with this graph theoretic metric. Khartoum is a little more challenging, and so on the left, you'll see something that we aren't doing so well. On the right, we're doing a much better job of capturing the structure. So again, not a solved problem, but doing a decent job. Something that we're pretty excited about. So I'll also make a note that OpenStreetMap, right, is a great resource that has labels a lot of places all over the globe, and that's something that is very useful. It's not complete in a lot of these unmapped areas, and certainly not something that's easy to update, right? As we saw earlier, right, remapping Puerto Rico after the hurricane took over 2 months, right? So if you can run on these algorithms quickly in a span of a few hours, this is something that could be very useful. So to drive that point home, this is something that we did, the SpaceNet partners, was let's take those lessons learned from those algorithms from SpaceNet 3, let's scale it up, right? So we had to chip things down to 400-meter tiles to make things easier for the competitors. That's not really that useful at the end of the day. What you want is a whole city. So let's scale these algorithms up and apply them over a whole city, and let's see how well we do. So this image is showing all the blue lines here are actually roads that were extracted automatically from just the imagery in Khartoum. We're doing this in a few hours, so this is something that you could potentially use as a base map that might speed things up markedly if you're trying to remap an area after a disaster or map something that hasn't really been mapped before at all. So SpaceNet 5, with that introduction, is looking at roads again, but in a little more detail. And so what we did right for the SpaceNet 3 was looking at the road networks and how you build that graph structure. But ultimately, what you usually care about, right, is actually the travel time, right? So probably many of you, this coming in here today, I looked at Google Maps and said, I think it's going to take X amount of time to get here. That's very, very handy to have. So Google Maps is a great resource. Google Maps doesn't always work in a lot of scenarios, right? Maybe there's not good maps, maybe no one has cell phones on them, so you don't have a traffic estimate. Maybe there's a natural disaster, so the cell phones are down, and you don't have any idea of traffic or even what road might be washed out, right? So if you could pull out this graph structure, the road network from imagery very quickly from a satellite, this is something that could be very useful if you don't have a good ground truth. If you can pull out travel times, that's even better. And that's what we're gonna look at is, we know some aspects of the road. We've had a pretty rigorous labeling taxonomy, so we can get a guess at the road speed. And we'll ask competitors to say, give us the graph structure and give us the actual travel time of each route. And then we can use that, of course, to do some really cool things going forward. We have studied this internally, so we have a baseline that we've run, and we're really excited to see how much better the competitors do, but we know something's feasible. So what we're showing here is, on the left is an input image, a test image, and the middle is a label. So in this case, like red is 25 mile an hour speed limit, green is 35 in blue is 45. And then what we're trying to do is predict those speeds, and that's what we get on the right. So not perfect, never going to claim that, but pretty darn close. And so there's utility here, I think, in actually saying, let's pull out those speed limits of the roads and actually do something that we can build upon from that. Also, we're kind of starting to kick around ideas for SpaceNet 6. And that's something that's going to be led, at least on the cosmic end, from our colleague Jake Schurmeyer, and then with a lot of help from the other partners. There's a lot of different options going forward here, right? So we've been really careful going forward with SpaceNet is to kind of take an iterative approach. Let's not bite off a huge challenge that might give us really terrible results and we don't really know why. But we're going to keep upping kind of the threshold of complexity. And so one is looking at kind of model deployability and generalizability. So at the end of SpaceNet 5 that we're labeling now, we'll have 10 cities. So that's a nice, diverse set. But we'll continue to kind of push that and keep expanding the number of cities. So deployability and generalizability is a really big problem. If you train a model on Shanghai, will it actually work in something like Khartoum? That's a question that we're going to look into. There's also new applications beyond foundational mapping, like change detection, for example. And there's different modalities, right? So we've so far looked at imagery in the red, green, blue mostly. But you have other things like infrared, maybe even radar that could be very interesting to look into. So I will stop there on my end and hand it back to Ryan.
And last but not least, before we kick off into questions, is that, as you're probably seeing a theme here, our goal is to get as much information out there as we can. And so the easiest link for a majority of this information is just go to spacenet.ai. From that, you can get into the data sets on AWS. There's a quick link to jump into the GitHub repository. Also, where we post a lot of analysis is on our blogs. So our Cosmics blog is the downlink with a Q. That's on Medium. We also have a mildly entertaining now podcast. I caveat the mild part. You can find that on any of your providers. That's training_data. Coincidentally, we also put those recordings up on YouTube. So if you want to watch Nick and I stare at each other for 35 minutes, you can do that. But with that, we'll turn it over to the audience for questions. And we really appreciate the opportunity to present today. Thank you.
Just a note, if there are any questions, please use the center mic in the center of the room. Thank you.
Oops, sorry. There we go. It's really interesting. There's a lot of cool stuff there. What I was curious about is, I don't remember all the cities that you had talked about, but many of the ones that you had talked about seem to be very flat. And I was wondering if you had considered looking at other cities that have lots of hills or mountains near them or things like that, and how much you think that might affect a lot of the algorithms that have been used in these coding challenges. Just a curious question, that's all.
It's a good point. So I think hills will be a challenge. Like I said, we're working hard to make sure there's a lot of diversity in the SpaceNet data set, so we'll have some more diversity released end of the summer. There's some like Rio is the first SpaceNet city that isn't all that flat and makes things a little more challenging. I think that the off-nadir piece actually is a far more tricky problem to handle. So that, I think, if you're close to nadir and you're hilly, it's not going to be nearly as challenging as flat and just a little bit off nadir, a little bit being 30 degrees or more.
You highlight a good point, which is, and this is something we've started to talk about in the context of 6, which is incorporating other information, clearly in the case of elevation, talking about digital elevation models. And that's, I think, something we would love to get into for future work. And I think we're finally, particularly on buildings, we're finally at a point, at least at Nadir, to see strong enough performance to start exploring bringing in a second data set.
Yeah, I'll just add real quick. I think, Adam touched on the point that our approach with this has been to, control some of the variables early on and then add complexity as we progress through additional data sets and challenges. So absolutely great point. It's something we want to, of course, have as much generalizability and diversity in the data as possible, but we also recognize that we have to kind of, we don't want to skew the results by introducing more variables than we're ready to handle too soon.
Next question.
Hello, great presentation. What would be your approach if you want to detect the breaches in these roads?
So that's a good point. There is some metadata that we're tagging in the road labeling, and one of those is if it's a bridge or not. So that's actually in the metadata. We aren't necessarily asking for that specifically from the competitors, but it'll be in the labels that are easily downloadable. So if anyone wants to look into that in more detail, it's there. And it's a big challenge, so that's an aside. Pulling out overpasses and intersections is actually really a tricky problem. And so labeling that is really handy to have. And that, I think, gives us a little more flexibility going forward, even if we want to tackle that problem specifically.
And if you'd like to help do any QA/QC on overpass data, please talk to us afterward. Sure.
Hey, first of all, really good stuff, guys, and thanks for sharing. I think the idea to do SpaceNet 6 on generalizability is great, and I very much support that. How will you ensure that people aren't just those still coding to the competition? Because I know in some of the prior ones, like if you look at the open source codes, there's if city equals Paris, threshold equals, right? And so like how do you ensure that the solutions are truly generalizable and people are releasing code that isn't just competition ready?
Great point. And so there's a lot of utility in these challenges, but if you're not careful, the results are not usable at all, right? That's a good point. One of the things that we are planning to do, certainly for 6 and I think for 5 as well, this is somewhat preliminary, so bear with me, is we're going to hold one of the cities back, right? So obviously there's a test set, but we'll have one or more test cities where no one knows what that city is except for us until we release it. So you can't just say, you know what, I know it's going to be Paris, so give me this threshold. You have to make something that's actually generalizable to actually get a good score.
Hello, I'm just curious, like for the images with the nadir angle, you said there was a problem that the accuracy drops when the angle increases. Is there any other use, like have the angle of satellite images but create the three-dimensional objects rather than the current two-dimensional labels or objects you're detecting at?
That's a very good point. So, in theory, if you have multiple angles, you can do something like stereo and pull out the 3 dimensions. That was something, so Core 3D was an IARPA challenge that wasn't using quite the same data, but very similar approach. So that was really interesting. We haven't tackled that yet, partly because we didn't have height information. And so without those labels, we figured it might not be that useful to try this. But you're absolutely right, 3D is something going forward that will be really interesting to look into further.
Another example of that is we're thinking about for 6, incorporating sort of the gold standards for icon. It'd be incorporating that into either some or all the SpaceNet cities that we currently have. It's still preliminary, though, on how exactly we do that. Todd, anything you want to add there?
Yeah, I would just say that we have seen some good success extracting building footprints when you have 3D. And so, it's something it's of high interest to us. The one reason, though, I think that, it's still valid to consider this without 3D data is that many times you may not have the multiple look angles that you would need to construct that. In the case of, say, like disaster response or other types of foundational mapping, we also, so I touched on the theme of controlling variables earlier, but it's also being able to have algorithms that'll work with the data that you have in a more of a real world context. So that's another point to consider as well.
Unless there are any other questions, we're all happy to entertain specific questions or deep dives after the talk. Once again, thanks to Amazon for the chance to present. Have a great rest of the summit. Thanks a lot.
Great, thanks.